In this video, I will review rational functions, and I'm going to do that in the specific order according to this plan that we have developed in one of the previous videos called Pre-Calculus Review. That is, I'm first going to review the prerequisites for rational functions um, in regards to operations, expressions, and equations that you have to know before thinking about rational functions, and then we'll figure out the details or the answers to the questions um, presented by each of these bullet points. So if you need more details on what each of this means, please watch that video called Pre-Calculus Review. So let's go ahead and get started with the conversation about the prerequisites. And when it comes to operations that one needs to be able to perform on when dealing with rational functions, here's the list. You have to be able to work with fractions because rational functions are extensions of rational numbers. So you have to know how to work with fractions, and you have to know how to evaluate this function for all values of x and for all polynomials in the numerator and the denominator. Now, when it comes to pre-algebraic tasks, you have to be able to perform factoring of a polynomial, because even though the name of the function is different, rational functions are made of polynomial functions. So you have to be able to work with polynomials. So you have to know how to factor, you have to know how to distribute it, you have to know how to combine like terms. However, in addition to all of that, you also have to know how to simplify rational expressions and how to do long division of polynomials. That comes really handy when doing certain things with rational functions. Now, when it comes to equations, you have to be comfortable with solving rational equations. If not with some arbitrary value c on the right side, but when that value c is equal to 0, you definitely need to know how to use the quotient property to find the solution set of this equation. You have to remember that the extraneous solution may pop up at some point. So again, I'm not here to teach you all of that, just to remind you. So if you need more details, let me know in the comments below. Now that we finished the conversation about the prerequisites, let's start answering all of these questions. And let's start with the conversation about the form. Rational functions can be written in 3 different ways. Standard form, it's named after the standard form of polynomials involved. Factored form, also named after the factored form of the polynomials that make this function. But in addition, we also have a quotient form. So here you should be able to take one polynomial divided by another polynomial, find the quotient, the remainder, and identify the divisor. So this is what we refer to as quotient form, and all of these 3 forms are quite useful when it comes to graphing. Now, you should know this vocabulary. You should know, for example, what it means to call a rational function proper or improper. And you should know that the simplest rational functions are called reciprocal functions, and they look like this. So they're pretty much the equivalent of polynomial, sorry, not polynomial, power functions in relation to polynomials. So whatever power functions are for polynomials, this is what the reciprocal functions are for rational functions. And graphing reciprocal functions is pretty easy. So the pattern pretty much depends on the value and the sign of the coefficient, and whether the power of the x in the denominator is even or odd. So when a is positive and n is even, we get the following shape. Here, what's going on in the middle is a vertical asymptote, and the end behavior is also asymptotical. And here we have horizontal asymptote. So those are the properties of these reciprocal functions. And here we have one with positive coefficient and odd power. again, we have vertical and horizontal asymptote, but different behavior. So there are 4 possible behaviors when it comes to drawing something with a vertical and horizontal asymptote. This is even n negative a, and this is odd n negative a. So it takes a little bit of effort to kind of make sense of all of these behaviors, but given the coefficient and the power, you should be able to sketch the graph of a reciprocal function relatively fast. Now, when it actually comes to sketching graphs of rational functions in general, what do we do? Well, we do it in stages. First, we analyze the end behavior using the standard form. We analyze the end behavior by pretty much looking at the leading terms and creating, and at this point, we don't know if it's going to be, in general, we don't know if it's going to be a power function or reciprocal function. It all depends on whether n or k are greater or less than another one. But you're going to end up with the reciprocal or reciprocal function or power function or zero, or actually, sorry, not zero, but a constant here. So depending on the scenario, you may end up with your end behaving like a reciprocal function or like power function or like horizontal asymptote or like slant asymptote. How do we find this M and B? We actually find them from this mx plus b thing will pop up right over here. So when you have a slant asymptote is when you have your quotient to be of degree exactly 1. So again, all 3 forms come really handy when you need to graph a rational function. Now, what can we learn from writing a rational function in factored form? We can learn the x-intercepts, and we can learn the behavior around x-intercepts by looking at these multiplicities. So for even multiplicities, the graph will be bouncing. For odd multiplicities, the graph will be crossing. Now, when you reduce your rational function and look at what's left over here, this is where you're going to get your discontinuities. So after you simplify it, what's left will give you a vertical asymptote, and around that vertical asymptote, your graph will behave in a way that depends on these multiplicities. So if this multiplicity is even, your graph will be, again, remember, you have an asymptote, so what are the possible behaviors? Your right side is up, left side is down. Right side is down, left side is up. Right side is up, left side is up, and right side is down, left side is down. So for even L's, both of your sides will be either up or down, and for odd L's, one side will be up, the other side will be down. Just figuring that out is enough for you to sketch a very decent graph by following these steps. So you determine the end behavior, you factor, simplify, and you identify your removable discontinuities. So if in the process of simplifying one of the denominators disappeared, that means you have removable discontinuity. You should be able to determine the local behavior around the x-intercepts following the multiplicities in the numerator. You should be able to determine the local behavior around the vertical asymptotes using the multiplicities in the denominator, and that's enough for you to sketch the graph. Again, I'm not giving you examples or any too many details here. As the format of this review doesn't allow me. So if you need more details or have questions, let me know in the comments. Now that you have the graph, you should be able to answer the questions about the domain and the range. The domain, again, is all real numbers except where the function is discontinuous, which is all the values in the denominator of the original definition of the function. The range of the function really depends on the combination of many factors, such as the local and global behavior. And actually, we won't be able to answer these questions without seeing the exact graph. Analytically, we can try to figure out some of it using the tools in calculus, but we just don't have enough skills in algebra to answer all these cool questions. Now, when it comes to intercepts, again, the Y-intercept, it's the output when input is 0. So you should be able to plug in all those zeros for x. The y-intercept in standard form is just the ratio of the free coefficients. The y-intercept in factored form is just going to be, and I missed it again. I'm going to type it here. It's going to be also -1 to the power, and the power is all the m's from the numerator, but also all the l's from the denominator. That's what determines the final answer here. So let me just finish typing it right here. So this is the correct answer. And the x-intercepts are obtained by solving the equation, but this equation is a rational equation, so we solve it by using the zero ratio properties, which says that your numerator has to be equal to 0. But since the numerator is a polynomial, then we solve that polynomial equation, and here are your x-intercepts, which we already knew. Now, again, reminder that rational functions are made of polynomial functions, so your ability to factor polynomials is crucial when working with rational functions. Now, continuity gets interesting here. This is the first time we actually have to talk about continuity and say things other than the function is continuous. Now, rational functions may have two types of discontinuities. It may have removable discontinuity, and it may have an asymptotic discontinuity. To determine which one you have to keep track of the zeros in the denominator, and as you're simplifying it, if it somehow disappeared, then at that value you had removable discontinuity. If you still have it, even if after you wrote it in the reduced form, then it is asymptotic discontinuity. So monotonicity is definitely not going to be any easier than it was for polynomial functions. And for polynomial functions, we left that task for calculus. We just simply don't have enough tools in algebra or pre-calculus. And I'm going to say the same for rational function. Like the determining monotonicity is closely related to the process of figuring out minimum and maximum or turning points. And this is something that we deal with in calculus. Rational functions are very unlikely to be one-to-one, very unlikely. But there are a couple special cases which you should know how to handle. This is the first one. So this is the simplest rational function that confuses a lot of students for some reason, sometimes. This is one-to-one, believe it or not. It's the simplest rational function. You should know how to graph it. You should know everything about this function. And you should know how to find its inverse. Now, looking at this inverse, and like you know how the coefficients here a, b, c, d, and then it goes a, b, c, d. So there's an interesting relation between how these coefficients align in the original and the inverse function, which kind of opens a couple new conversations later on. And this is another example of another odd function. Sorry, not odd function, but a one-to-one function when n is odd. And you should be able to isolate y in here after swapping x and y and producing the inverse function. So again, in general, no, but in these two special cases, yes. When it comes to symmetry, in general, rational functions are unlikely to have symmetry, but you've seen the reciprocal functions. And if you look at the reciprocal functions, those are special cases, right? This is odd, this is even. This is odd, this is even, right? Those are the types of symmetries we have. And look at the coefficient here. Sorry, not the coefficient, but the n. When n is even, the function is even. When n is odd, function is odd. So there's a connection between those coefficients and why we call functions even or odd. So again, symmetry in general, no, but for simple reciprocal function, yes. And not just yes, but there's a beautiful connection between the name of the symmetry and the one of the parameters of the function. Now, special features of rational functions. Rational functions are large class of functions that contains all of the functions that we learned before except the absolute value functions. So linear functions, quadratic functions, polynomial functions are all sit inside of the rational functions class. And as such, it is definitely worth studying. Now, in addition to that, it's the first function that we had that had a discontinuity, right? That's also making it interesting. And also, it's the first function that had asymptotes. That's also pretty cool. Not all functions have asymptotes, but this one may have vertical and horizontal and slanted asymptotes. All right, when it comes to finding equation, in general, it's going to be incredibly hard because even if you set up a system of equations, your equations will not be linear, and as such, they're not going to be easy to solve. Well, actually, they are linear. Yeah, actually, they are linear. So the system is linear. It's definitely linear because you can simplify it. You can make it linear, right? And not only linear, it's going to be homogeneous. So I think it is possible. The only thing I'm not sure is whether you're going to have a unique rational function for each combination of points. I'm not sure about that. But in general, this is something that we probably never done in algebra and probably will never do, but it is possible. All right, finally, when it comes to applications, rational functions, like graphing rational functions, it's such a great task to practice one's analytical skills. Like literally, given all those constraints that we can figure out from the standard form and factored form, it like actually producing the end result. It's definitely not an art. It's not a piece of art, but it's a very analytical process that if you master it, you should be proud of yourself. This concludes the review of rational functions, and the purpose of this review was to just remind you of the answers to some common questions about rational functions. If you have more questions or if you need more details about the answers to some of the questions, please let me know in the comments.